Video, we're going to discuss the workflow involved in training a deep learning model on a GPU. We're going to look at single GPU training and then move to the multiple GPU training using strategies called DDP, distributed data parallelism. Then we are going to discuss about the limitations of DDP and discuss some of the better strategies which are generally used in training very large models. Before we move further, let's define some conventions. So in this particular video, we're going to use this as a representative of input sample, and then this as a representative of the model graph. And we're assuming the model graph is directly fetching us the loss value. And if we pass multiple samples, we get multiple loss values. So each of this circle represents the loss value. And then each of the small cuboid represents the gradients of the loss with respect to the parameter. Not that we have colored the input sample, loss, and gradients with the same color, which indicates that these are specific to some particular sample. So if you have multiple samples, there would be multiple such colored things. Let's move now. Okay, let's come to the single GPU. So in single GPU, we when doing the forward pass, we have this, let's say, 4 images. We pass these 4 images through this model graph, and we compute the 4 loss values each for this image. Then in the backward pass, we calculate the gradient of each of this loss with the parameter. So if we have 4 losses for 4 input samples, we'll have 4 gradients. Then we combine these gradients and take the mean out of them, and we have the single gradient. And in the parameter update step, we update the model weights with the gradient, with the use of gradients and other things, depending on your optimizer which you're choosing. You can use whatever optimizer you like. General popular optimizer, Adam, is very common though. And then we get this new model state. Now we, in the second batch, in the second step, we have this new model and these 4 new samples, which we pass to the model and do the computation. Let's move, and we'll just repeat this process again and again. Now let's move to the multiple GPU training. So in multiple GPU training, we first specifically distributed data parallel. We are discussing distributed data parallel only. So we create the multiple copies of the model on the multiple GPUs. So in this case, let's say we have these 2 GPUs. We create 2 copies of the model, and then we distribute the batch, which is 4 in this case, on these GPUs. So each of the GPU would get 2 samples. Now each of this GPU would process its sample, do the forward pass, and get us the loss value as shown with these circles. Then we do the backward pass, in which we calculate the gradient of this loss with respect to the parameter independently on both the GPUs. It's very similar to the single GPU thing. But the main thing is that now we are having multiple GPUs, so each of the GPUs is going to do that computation independently. But now, for calculating the average, the overall gradient of this particular batch, we'll have to do some kind of synchronization. So up till now, the GPUs are free to be, like one of the GPU is free to be ahead of another, right? But at this step, all the GPUs should have computed the gradients. So now we are going to have some kind of barrier here to ensure that all the GPUs have computed the gradients. And once all the GPUs reach there, we calculate the average of these gradients across the GPUs. So some data transfer happens across GPUs to calculate this gradient. And then this gradient is replicated over both the GPUs. Now each of the GPU updates its own model state using the gradients. Not that, again, here there is no synchronization involved. The only way the model is synchronized is because we started with the initial state, which is same for both the GPUs, which is this blue cuboid, and then we had these gradients, which are also same for these 2 GPUs. So that's why we get this same model weights at the end. Now we just repeat this procedure again for the second batch which comes, and then just repeat the following steps. This is how typically multi-GPU training happens in common frameworks like PyTorch or TensorFlow. Now let's try to think about the limitations of DDP. So note that in this DDP, we are duplicating the model states and optimizer states on multiple GPUs, which is definitely introducing a lot of redundant memory, right? And we can't really train very large models if the models can't be fitted in a GPU memory. So there comes the advanced strategies called model parallelism and deep speed. In model parallelism and deep speed, we typically split the model weights onto different machines. So in distributed data parallel, we had one GPU, every GPU having the same complete copy of the model, right? But in model parallelism and deep speed, we distribute the model weights and optimizer states across multiple GPUs. So each of the GPU will have only the partition of the model as compared to having the complete model. And in the more real world setting, if someone wants to train a large model, they typically combine all of these strategies: model parallelism, deep speed, and distributed data parallel. As you can clearly see from this graph, that we have reached a new era of machine learning, deep learning, where we want to train very large models, up to 530 billion parameter model. These models cannot be definitely fitted into a single GPU machine. So we split these model using these advanced strategies, combining model parallelism, data parallelism, deep speed, and whatnot. Thank you.